physical processes like the transport, diffusion, dispersion, and then like thermodynamics and stuff like this. But it's all about how these things affect microbial growth and microbial activity. I'm going to start with a little bit of introduction, quick one. Just for that, I need to find. Okay, to keep the time. Sorry about that. Okay, so about salt caverns. Well, I think most of you already know why we use salt caverns for hydrogen storage, basically, in the times of excess energy, usually from fluctuating energy sources like wind and solar. We need to store this energy, and hydrogen is a great energy carrier. And salt caverns is one of the options, probably the most technically advanced and the risk option for underground large-scale hydrogen storage as an energy storage method. Where do we make this salt caverns? Usually there are like salt formations in the form of salt domes, and we create these large cavities within these salt domes, and we call them salt caverns. And how we create them is called leaching. Usually we drill a well, we circulate water, it dissolves the salt, and we produce the water, and this cavity grows. But after we do the leaching, we debrine the water, we take out the brine from the salt cavern, but usually there is some leftover brine accumulated at the bottom of the salt cavern, and the rest of the space is used for hydrogen storage. And in this brine, usually there is insoluble debris accumulated at the bottom of it, and this is important for us. You'll see why in a bit. So I want to basically start the main presentation by telling you the story of how all this idea came into existence. Basically, there was this one evening when I was scrolling through LinkedIn, and I saw a few posts by Nicole, who works with microbiology in hydrogen storage. They were advertising their paper, and it was about microbial life in salt caverns. And that was very surprising to me. Back then, I hadn't worked much with salt caverns. If you asked me, I would have said like the salt cavern environment is too extreme because it's too saline for microbes to grow or grow enough to matter. But apparently it's not, because I continued reading a bit and I saw a few more papers from Nicole and also papers from other authors who have been discussing and measuring microbial activity in salt caverns. So it's not extreme enough to suppress all microbial activity. But the next thing that came into my mind, by the way, I am an engineer. I am a reservoir engineer, not a microbiologist. So the first thing that came into my mind was that this huge body of water that we have here, and when I say huge, it's like normally around like 50 meters high, like tens of meters, like 80 meters wide. If the microbes are growing in this brine, in this swamp water from now on, I will call it, then well, where does the nutrients come from? And what are the nutrients? Basically, there is the hydrogen on top, which has to be transported through the water. And also there are minerals, specifically like sulfate and bicarbonate, that are being dissolved from the formation and then have to be transported to where the microbes are living. And most of these papers mention that this body of water is basically where we expect the most microbial growth to happen. But if it's that big and it's stagnant water, then diffusion is the process through which these nutrients are being supplied to where the microbes are living. And well, my intuition tells me diffusion is slow, especially when there is such a big body of water, and also there is such a small surface to volume ratio for this water compared to porous media. So I expect not much of especially hydrogen to be diffused deep enough for microbes to be growing fast around the bottom of the or the body of this sump water. I continued reading a little bit about it, and I realized like there are different locations where it has been suggested that microbial growth can happen. If we have this kind of cavern, we have these insolubles at the bottom, and well, a lot of microbes prefer a solid surface on which they can form biofilm, and that's their preferred way of life. So the formation of biofilm on this porous media of the insolubles at the bottom, on the walls of the salt cavern deep inside this body of water is the first one. The second one is the body of water itself. Well, planktonic bacteria, the bacteria that don't need to create a biofilm, are swimming around and consuming hydrogen. Then there is the surface, and then there is the intersection between the water, hydrogen, and the rock surface, which already looks like the best place because they have water, they have hydrogen, and they have the solid surface and the minerals all at the same place. Then also, it has been mentioned that outside the water phase, on the walls, there could be microbial growth. Well, what is basically the limiting factor is expected to be water here, but we will talk about it a little bit more. And also there are microfractures or micropermeable layers that intersect the salt cavern, and well, microbes can grow in that porous media close to the cavern. What I'm going to talk about here basically is to evaluate this intuition of mine that in especially zones 1 and 2, deep inside the water on the solid surface and inside the bulk of the water, diffusion will limit microbial growth. It cannot be a considerable amount of hydrogen diffused deep enough to matter at all. And in order to do that, I started doing a little bit of modeling, a very simplified, quick way of just getting an order of the number of how much hydrogen can diffuse through this sump water. So I had two main assumptions. First of all, I want to see how much diffusion is limiting this microbial growth. So I'm assuming that microbes are growing way faster than the supply of hydrogen on the boundaries of each of the models. So whatever hydrogen is being supplied is being consumed quickly. And I assume that the transport of hydrogen from the gases into the water phase at the surface is instantaneous, and the limiting factor is the diffusion of hydrogen within the body of water. A simple Fick's law, which gives us a kind of simplified way of calculating diffusion. If I want to calculate the rate of diffusion down to the bottom, I use basically a linear. It's going to be a linear profile of concentration and a constant rate. And if I want to calculate it on the walls, it becomes a little bit more complicated, a simple integral. So analytic solutions, nothing complicated. And here I'm going to show just a little bit of the results. I'm not going to go into much detail about these results, but these are basically how much hydrogen, what ratio of the stored hydrogen are being consumed in different places, number 1 and 2. This dashed blue line is the bottom of the sump water, and this dashed red line is the walls of the salt cavern within the sump water. And this black line is the summation of the two. And as you can see, for a normal salt cavern, which is usually around here, this is the height of the sump water, which is from a few centimeters to a few tens of meters. The ratio is so small. This is in the order of -4 or 5. So it's negligible. And I continue just doing calculations with other assumptions for other um, storage pressures, and also for within the body of water for planktonic bacteria. And basically, the main message did not change. The diffusion cannot supply a considerable amount of hydrogen in locations deeper than a few millimeters in the saltwater. Where I mean, the intuition was correct, basically, but I couldn't say like how much. I would have said like a few centimeters, but based on these calculations, even a few millimeters deeper into this body of water is where the supply of hydrogen is very limited, and it's not gonna matter in the long term for how much hydrogen is being consumed. Well, at this point, I showed my calculations to a colleague to check out the zeros and stuff like this to make sure the numbers are correct. And I was proud because my intuition was correct. But then he mentioned that, well, I shouldn't be proud because I basically killed the topic if we can so simply conclude that it doesn't matter there, what do we have to study? So at this point, I had to actively try to prove myself wrong. And what was wrong about what I did so far? Basically, I could go on looking at the other locations. This one was only the number 1 and 2 in the graph I showed, basically the um, bottom walls and the body of the water in the sump brine. But I didn't talk about the surface of it, 3 and 4, and outside the sump water. And the other thing I could do to prove myself wrong is to basically go question my assumptions, which I will get back to in a while. But first, going back to looking at the other location as well. I already said that these two don't matter. 3 and 4 are probably the best ones, and I don't have like an intuition about them, but now I can tell that they are a few millimeters maximum deep. So I want to also look at number 5, where water is the limiting factor, and see how microbial growth can happen there. And what's limiting there is as I said, water. So what's supplying water there is basically evaporation and condensation of the on the walls. In order to just have a quick analysis of how probable is condensation on the walls outside the sump water, I needed to look at the thermodynamics of hydrogen. And well, that's when I learned that hydrogen is such a weird gas. First of all, its compressibility is so different from other gases at normal temperatures, like 27, even minus 100 degrees. It never goes below 1. This is for hydrogen, and these are for like methane. And more importantly, the Joule-Thomson coefficient for hydrogen is negative. It means basically when you compress hydrogen instead of warming up like a normal gas would do, it cools down. And that changes everything in terms of condensation and evaporation in compared to a methane storage salt cavern. This is where we just had a like quick analysis of when during withdrawal, shutting, injection, or storage, this condensation can happen. So we looked at changes in pressure, temperature, and humidity in the gas phase. An important thing I need to mention here is that this is with the assumption that the whole gas phase is fully mixed and uniform. So these blue areas, like here and a little bit here, are where this temperature pressure conditions change in a way that we have supersaturated gas phase, supersaturated with the water vapor. So that's where condensation can happen. Or if I want to be more accurate, that's where misting can happen. Because the walls are expected to be a bit warmer than the gas phase, it might not be condensation on the walls, but misting can happen, and that also can be something to supply the water. But here is basically where I'm going to question all the assumptions I had so far and what we will need to study in the future. As you can see, this presentation was not much about giving you answers or conclusions. It's much about posing questions. Well, this is the temperature profile of the geothermal gradient in a salt formation, and this dotted line is what is the reality, almost what is the reality in a salt cavern. Well, first of all, the water that we live in the salt cavern is considerably colder than the formation around it, and it takes years, several years, for it to warm up to the temperature of the formation. So it's going to be much colder than the geothermal gradient. And on top of it, here it cools down the gas, and so there's an area here where you expect no convection in the gas phase, no natural convection in the gas phase, and then there is where we expect natural convection. In order for us to just understand whether natural convection happens in each of the phases, there are basically two conditions required. One is that the adiabatic gradient of the fluid is less than the geothermal gradient, and the other one is that viscosity cannot impede natural convection. Well, for these big bodies of fluids, viscosity wouldn't matter at all. And basically, this first condition also applies for both gas and water phase. So we expect natural condition to happen. But as I mentioned, at the bottom of the gas phase, on top of the water phase, there is no convection. So that assumption basically that the whole gas phase is fully mixed was definitely wrong, because within this zone, the water vapor has to diffuse upward to reach where there is convection and mixing happens. So it might not be supersaturated as fast as I expected. And also, there is natural convection within the water phase, so diffusion is not the only thing that causes mixing and transport of hydrogen and nutrients to the microbes within the water phase. There's not much studies where they have measured the rate of natural convection, but the few ones that do show that that rate is not really that big, and it's way more complicated than just having a spiral flow all over the salt water. So what does it mean? It means we need to do much more detailed studies on this. And in our studies, we need to consider the interplay among the kinetics of thermodynamic, transfer, and biochemical processes. So we need to have multi-scale thermohydrobiochemical modeling that consider all this the kinetics of all these processes. And there are also some processes that I did not mention here, but definitely needs some more studies. First of all, the availability and transport of nutrients like sulfide and bicarbonate in the thin film of condensed water, because when condensed water is on the surface, it flows down and there's a thin film left behind. And is that thin film enough for microbial growth? Or if it's local, is there enough dissolution of these nutrients for microbial growth? And also the transport in it follows a different laws than transporting big bodies of fluids. And also there's microbially induced convection, especially on top of the water phase, where microbes can flow. How, in what scale does that matter, and how much convection can microbial activity create? That's a big question. And also the dissolution rate of minerals. I did not consider that at all, and I don't know if that could be a limiting factor. There's also something that I would suggest to microbiologists in the room, nothing I would be studying, but it's important that other than studying the ability of of microbes in how fast they can consume hydrogen, see their lifestyle, whether they want to form biofilm or they prefer planktonic lifestyle, and if they can survive on the slightly wet salt surface and stuff like this could be really interesting. Well, thank you very much for the attention. And as I mentioned, I asked more questions that I answered here. So there's a lot to be studied. And if anyone wants to study them and collaborate on them, here is my email.
Thank you, Ali. That was excellent presentation. I'll just go to question around the room first here, then online people. Is there any question here?
Ali, could you go back to your to the graphs?
Sorry, could you say that again?
Yeah, you had some modeling results fairly early on. Yeah.
Response?
Yeah, exactly. So you got an interesting edge effect when on the right in at least 3 of them.
This ones you mean at the end?
Yeah.
But basically, yeah, here when you have like the height of the sump water as the x-axis, basically at this point is where the total amount of hydrogen stored becomes very low and reaches 0, because if this is 1 or if this is like 300, which is the height of the salt cavern, then the total amount of hydrogen is basically 0, and this is the ratio between the lost amount of hydrogen and the total stored hydrogen. That's why this effect happens.
Right. In a normal operational condition for hydrogen energy storage, so these big caverns that you describe, like possibly 300 meters deep and 80 meters wide, is the intention for them to ballast with water, or will they be operated dry with a big change in pressure?
Well, the intention is to use them as we need them, as much as I understand. I realized, like in one case, there was a shortage of hydrogen to fully fill the whole cavern, and they were planning on keeping it like 2/3 of it filled with water and only 1/3 used for hydrogen. So that, I mean, this, for example, can happen in a case like that. But I think if you have enough hydrogen and you need storage, then we are around here where it is like a few meters or tens of meters.
Okay, cool. And then in your sort of thematic model that this is based on, you showed all the cations, but you didn't show the potassium, the sodium, the lithium.
Yes.
Do they compete with hydrogen?
Could you say that again? Sorry to interrupt.
Or do those metallic ions compete with the hydrogen?
I don't know about competing, but I can say they are definitely very important to be considered. But here I have simplified everything. First of all, the mathematical model I showed and the calculations I made is with the assumption that all of these are already supplied and it's only hydrogen that's limiting. But if we go on considering sulfate, bicarbonate, and as you mentioned, like that, maybe nitrogen source and phosphorus source and stuff like this, then it gets more and more complicated. And yeah, we need to see which one is the limiting factor. But basically, the results I showed were only the diffusion of hydrogen, nothing else.
Great. Okay, thank you. Very nice presentation, by the way. Thanks.
Thank you.
Any more questions here? Any questions from online people? I could see a hands up. If any. Oh, Amir? Yes, please go ahead.
Thank you, Ali. Ali, thanks for your presentation. It was very interesting. Maybe you have already answered this question because I missed the early part. Uh, Putting aside the difference in type of, fluid, hydrogen, in this case, and looking back into methane storage or natural gas storage in general in salt cavern, which has a very long, history. So have you, you know, uh, learned something from natural gas storage in terms of, microbial activities, in that case, consuming, methane, um, to be used in hydrogen storage?
Mhm. Well, I'm not a microbiologist, so it's I'm not really comfortable talking about the details of microbiology here, but I would say it's a it's pretty different. Um, I mean, I don't think I know of like specific strains that can uh, use both methane and hydrogen as either electron donor or methane as carbon source. So I don't know. Really, there are not any interesting comment on that question. Sorry.
No, that's okay. It's just again, I'm not a microbiologist, just trying to learn more. Thanks.
Thank you, Amir. Is there any other questions online? Okay, so I'll ask a question. So in perfect world, if you could get some like a ideal experimental data that help your modeling to build up and like very close to realistic one, what sort of data you would need for your model? What would be the like a perfect experiment for your to improve your modeling?
Okay. Thank you for asking that question. Actually, we are about to start some experiments with a new PhD student who uh, will actually create some rather simply, but experiments in basically what we need to look at is to how much mixing is affecting our experiments. So all the, for example, bottle experiments where you have a body of water where microbes are growing in, uh, well, we need to look into like if you have a full mixing or if you have no mixing at all or even partial mixing uh, that represents natural convection, how much does that like change the uh, results? Also, I came across with some experiments. Somebody mentioned to me that they are doing is to have like um, blocks of salt rock that is partially in the water phase and partially out of the water phase, and looking into the like how microbes are behaving. Are they growing on the surface of the salt outside the water phase or not? But for that, we need to very carefully um, basically manipulate the evaporation, condensation, and changes in temperature to make sure the condensation and misting that is happening makes sense compared to a real case. So yeah, I can think of like a lot of experiments that would be perfect, but um, yeah, it's gonna take a lot of work.
Yeah. Thank you very much. If oh, one more questions from Andrew.
Yeah, something that certainly maybe you said was quite strange was the inversion of the Joule-Thomson effect. Are you totally sure about that? And I mean, for a covalently bonded dihydrogen, why is it?
Sorry, are you talking about this here? That this change here?
No, you showed the Joule-Thomson effect for
Oh,
hydrogen.
Jules Thompson. Okay.
It's cooling rather than
Yes,
warming.
actually, yes. Thank you for this question. Actually, whenever I present this stuff to like my petroleum engineering colleagues who don't have much like experience with hydrogen, they always question this. Are you sure that like hydrogen has like negative Joule-Thomson coefficient? Yes, I'm pretty sure. And yeah, if you look for it, you can see a lot of interesting stuff on that, both about the compressibility factor that never goes like below 1, and about the Joule-Thomson coefficient that is below 0 mainly. So yes, and it has been like discussed a lot, I guess, also in terms of how the small, very light and fast molecules of hydrogen create this effect. I don't feel confident to go that deep and explain that, but if you just Google it, you can find amazing stuff on this and how it's different between a very light gas like hydrogen and even helium a little bit compared to like methane and CO2 and air.
Yeah, even like in this hydrogen car fueling stations, because when they fuel the car, it heats up the car because, and then that's why in the fueling station they keep hydrogen like in -20, so the car won't explode when you.
Yeah, so also something is interesting about that. That's one of the things that make hydrogen very dangerous, because if it leaks and it expands, it actually heats up. So it can like explode easier than methane would, because methane cools down, but hydrogen heats up.
Thank you very much, Ali. That was excellent presentation. And hopefully this was the first of many meetings we will have in this GIGNet. And thank you for doing the first presentation of this GIGNet and this year. And thank you everyone for attending as well. And I hope you have a very nice day. Thank you, Ali.
Thank you. Thank you for this. Have a good day. Bye-bye.
Thank you. Bye.
Thank you.